With the development of the aviation industries and the improvement of people's living standards, more and more people choose airplanes as the way of travel. However, airlines adjust price in real time according to the revenue management system, and the ticket price changed significantly. The feature of the fluctuations make price prediction extremely valuable in practical application. This project proposed the use of a time series algorithm for modeling designs and implement of a time series-based air ticket prediction algorithm, and compare and analyze the prediction results with actual travel website price, indicating that the model can provide passengers with more reliable decision-making support for ticket purchase and provide travelers save money. This project discussed three regression models for predicting airline ticket price: key neighborhoods regressors, decision tree regressors, and SVR. According to the data characteristics of air ticket price, the time series ticket price, and then the regression models is used to adjust it. Among them, the decision tree regressors performed the best. Since data is form of Excel field, we have to use pandas read Excel to load the data, and after loading it, it is important to check new values in the columns or the row, and if it's present, then following can be done. And before we train the model to predict ticket price, we need to do some preparation. After importing dataset, we need to do data cleaning. As a matter of fact, I will introduce process of data cleaning in this part. Our data information is stored in Excel, including the airline, source, destination, route, and duration, total stops, additional information, price, general day, general month, departure time hour, departure time minutes, arrival time hour, arrival time minutes, and there are some examples of the dataset. As shown here, most of the data types are not integrates, but we need to convert the data type to integrate so we can use the data to train the model. For example, the data types of the date of the journal, arrival time, and the departure times is object. So firstly, we convert them into data and time for proper prediction. And this method will extract only date of the date, and this method will extract only the month of the date. And now we extract the date and month from the date of journey and stored in two other columns. Then there will be no use of the data journal and data journey and column, so we drop it. And also from the arrival time and departure time features, we can extract hours and minutes and stored in new columns. After that, we drop useless columns. We applied pre-processing on duration column and support duration hours and minutes from duration. And here we check if the duration contain only the hour, because if duration only contains hours, it is a non-standard format. So we add 0 minutes after the hours. And we use two and there's the some results then and there's some items that now is integrate or not integrate. And we are using two main encoding techniques to convert category data into some numeral format. From graph, we can see that Jet Airways business have the highest price. Apart from the first airline, almost all having the similar medium. And as airline is normal categories data, we will perform on-hot encoding so that we can get this kind of table. And after this process, we can get finish the data cleaning so that you can use the data to train the model.
As we all know, machine learning takes a significant role in predicting information or doing something. In our fly fair prediction model, the project we should choose a machine learning model. Machine learning models are broadly classified into supervised models, unsupervised models, and also possibilities models. The well-known linear regression and neutral work models are all based on supervised machine learning models. So from the perspective of the number and the nature of models, we can divide the machine learning models into trained and verified single model and a sample model. A single model is trained and verified independently with only a certain model, such as linear regression and logistic regression models, etc. The integrated model is combination of multiple independent models to form a mixed model. That is to say, making the model more reasonable than the single model, such as random forest and other models. From the perspective of the supervision types, machine learning models are divided into supervised model and unsupervised model. The unsupervised model refers to the model learned from unlabeled data, while the supervised uh, machine learning model needs to learn according to the input and the output of the data during the training process. For our air ticket prediction model, we need to select an integrated and supervised learning model to get the best present results. In terms of air ticket price data verification, we use some other algorithm called R2 score index, and we can observe the difference between the real value and the predicted value, and then adjust the model the parameters of the model the algorithm to further improve more fitting to the model. Now I will discuss the random forest algorithm, and my partner Tang Yishuo and Zhou Shuyan will introduce k nearest neighbor (KNN) and support vector regression (SVR) algorithm model respectively. Okay, now the random forest algorithm, we call it RFA, is an integrated learning algorithm based on decision tree. We can see that the estimator is actually is the decision tree. Is there are many individual decision trees, which core is to train multiple estimators through the integrated learning and integrate the results of these estimators as the final output, as the graph shows here. Multiple decision trees selected different inputs through the random sampling, which has the advantage of greatly improving the robustness of the algorithm, obtaining outputs more reliably and reducing the interference of the outlier data. We also call it noise. At the same time, the random forest algorithm can be parallelized more efficiently since there are many individual estimators, and more conveniently, and those estimators do not conflict with each other. Although the parallelization is not used for acceleration in our FlyFire project, but it can be do it. So this is another one of the advantages of random forest algorithm. The specific process of the random forest tree algorithm is to randomly select the different data in the data set multiple times and input of the decision tree. Let each group of data select the optimal solution through the decision tree algorithm, and finally integrate multiple optimal solutions to obtain the final result. Take a very easy example. Input has an array of the number 1 to 11, and we use the RFA algorithm to do it. The RFA algorithm first randomly selected some of the data which do not conflict with each other to the different estimators and then use the decision tree algorithm. Each algorithm use decision tree algorithm to obtain the best choice via those numbers. Then the combiner use some extra algorithm. Actually, in very simple example, we just choose simply take the average or weighted average through those answers from estimators. Say the average of 3, 6, and 0, which is the result of those estimators, and make it to the average 3 plus 6 plus 9 and divided by 3, which is the final output should be 6. So this is a very easy example. And in our project, we choose the weighted average algorithm as the final estimator, as the final combiner, so that the result should be more reliable and more accuracy. For non-special regression problems, the final integration, say the packages that our project set in the sklearn, usually takes the average as the final result. And in our project, we counted the impact indicators of different parameters on the final price and finally calculated the result of different decision trees by weighted average. And this code is the way to act as the sklearn and use the package of sklearn to do the prediction. This code just use the average, not the weighted average algorithm. We can see it here is quite simple and returns the value. Oh, sorry. And in our project, we called the weighted algorithm. We calculate all the parameters, the weight of the parameters, and calculated the weighted average. Compared with the other algorithms like the SVR model or KNN, CNN, and some other algorithms, the random forest algorithm granted decent and other algorithms can avoid overfitting when the noise is not too large. Thus bring better performance while reducing the numbers of apples in relative training, and the backing algorithm in the decision tree can significantly reduce the correlation between multiple decision trees. Therefore, the random forest algorithm RFA can usually obtain higher prediction accuracy for training unrelated datasets. which is uh, correct, right to our project. And our air ticket model prediction project contains information on multiple departures and destinations, and there's no correlation between this information. And a single model, just such as a linear regression model, is difficult to accurately predict the information. Therefore, the integration of random forest model, um, uh, the model can train this data more reasonably. It can be predict that the random forest model is very suitable for predicting multi-region air ticket information. And also the fact is that the RFA algorithm to predict the airfare has an accuracy of over 90%, actually it's 93%. And as you can see later, uh, the accuracy of SVR algorithm is really low. And also the algorithm of KNN algorithm is not so good as the RFA algorithm. So as you can see, the RFA model is better. So this is all of uh, the algorithms and the RFA random forest algorithm, the introduction of this.
Okay, this part I will introduce you about a model called SVR, the support vector regression, and this model is also called a tolerant regression. So the first problem we want to know is about why SVR called the tolerant, why we call it tolerant. So first, we know the strict linear regression is like the traditional linear regression use a linear function in vector space to fit the samples. So the model takes the combined distance of all samples, actual locations to the linear equation as the loss and find so use the loss to minimize the loss, find the parameter of the linear function. Uh, a sample in the strict linear regression is counted as loss whenever it does not fall exactly on the linear function used as a model. So uh, the model a function of the support vector regression is also the linear equation. We can see that in this problem, we set the target function as y equals to epsilon x plus b. So, but compared with the traditional linear regression, as we mentioned above, the differences lies in the different principles about calculating the loss and the different objective functions and optimization algorithms. SVR creates an interval zones on both sides of the linear functions. The loss is not calculated for all samples. That only the samples falls out of outside the interval band. You can see this line. Um, in the middle is our target function, and by the side is our, and by the two side is our, isolation bands. So only the samples outside this band are included in the loss function. So why this is the reason why we called the SVR as the tolerant linear regression, because uh, you can see in this graph we only the samples with circular and diamond shapes, as shown in the figure below, are included in the final loss, and and the uh, and we wish so the naturally we according to the principles of we want we want to maximizing the isolation bands, minimizing the total loss, because we want to make as much as possible the samples can isolate locate in the how do you say that, isolation band. So uh mm, thus the SVR problem can be formalized as you can see this formula is our optimization objectives. And SVR will introduce two slack variables for many sample uh, x, both both this variable and this variable, if it is inside or on the edge of the band, so that these two variables uh, um, equals to zero both at the same time. But if a point that is above the upper edge of the band, so that this variable is this variable, we can use a pen like yes, this variable, this equal to 0, and this greater than the 0, so that in these conditions, this sample is below the edge of the spaceband, and when this greater than the 0 and this is equal to 0, so that under this condition, the sample is how do you say that, above the upper edge of the band. So we can convert these principles into this formula. After introducing two variables, we can rewrite optimization objectives to this formula, because we have the slack variables. So step 1 is about how to obtain the above optimal optimization. We introduce the Lagrange multiplier. You can see that ui greater than or equal to 0, and this variable also and this are all greater than the 0 or equal to 0. And step 2 is about when we have the Lagrange multipliers, and we can construct the Lagrange functions. You can see that this complicate functions is the functions we construct, and we can utilize it in the next step. And the mention about this equation, we can convert it to the same questions is like this. And in order to solve the Lagrange equation, we can solve this problem because these two problem is like the same. So the first part that needs to be addressed is minimization. We first do the minimization about this part. Yes, and for the so that this problem can to solve this problem, we finally we because we want to try to solve the how do you say that, minimization part, right? So then find the partial. We introduce the SMO algorithm is for the case where to solve the SVR. We need to first and then find the partial derivatives for several variables separatively, and make the partial derivative equals to 0 is that these four equations. Finally, we use the SMO algorithm to solve the SVR. And AI like this looks like as A, okay, and these two variables, and to also need to be transformed into one parameters before using the SMO algorithm, because the SMO algorithm is for the case where any sample X correspond to only one parameters, this only one this, and this process using the Lagrangian pairwise method, and the sufficient condition for the pairwise problem to have a solution is to satisfy the KKT condition, where is as follows for the pairwise problems of SVR. And you can see these 6 equations is the KKT conditions. We must satisfy or guarantee these 6 equations. You can see that we must guarantee that if we want to let this variable cannot to be can be the non-zero value, so we must have to make these equations equal to 0, and these conditions can same as this. That means that the in the null condition, the samples is under the lower edges of the isolation band, and compared to this equation, and this equation is when the conditions that when we want to let this variable can be the non-zero value, so we must let this part be 0, so that we have this condition. That means that the sample is up here, is above the upper edges of the isolation band. So we know that a sample cannot be the above the upper or and below the lower edges, and at the same time this condition is impossible. So so that we can conclude that the variable this one and this one can only want to be um if if uh if this one not equal to 0, then we must have this one you know the other variable must to be 0 and vice versa.
So in this part, we will introduce the KNN algorithm. First, we need to understand what is regression problem. First, a classification model is essentially the same as a regression model, in that classification model discretes the output of the regression model. So, in general, regression problems are usually used to predict a specific value, such as predicting the price of a house, future weather conditions, and so on. Just like the problem we want to solve if the price of a ticket is 500 yuan and the predicted value is 499 through regression analysis. Then we think this is a better regression analysis. And the regression is an approximate prediction of the true value. So in simple terms, the quantitative output is called regression, or continuous variable prediction is the regression task. A qualitative output called classification or discrete variable prediction is a classification task. So after understanding what the regression task is, we need to find out what is KNN algorithm. KNN algorithm, K nearest neighbor algorithm, which belongs to supervised learning. It is a basic classification and regression method. And from its name, it can be simply and roughly considered as k nearest neighbors. And when k is equal to 1, it becomes the nearest neighbor algorithm. That is to find the nearest neighbors. But why do we need to find neighbors? Let's say, suppose you come to an unfamiliar village. You need to find neighbors with similar characteristics to you, and you need to integrate them. So the KNN algorithm, given a training, can be used not only classification but also for regression. By finding the k nearest neighbors of a sample and assigning the average of some attributes of these neighbors to that sample, the value of the corresponding attributes of that sample can be obtained. So the KNN algorithm, given a training dataset for a new input instance, Find the k instances in the training dataset that are closest to the instance. And if most of these k instances belong to a certain class, then the input instance will be classified into this class. And for the regression problem, we can get the value of this as a k neighboring instance. The value of our input instance can be the average of the values of k neighboring instances. So we can know that the classification decision rules in KNN algorithm. Classification decisions in KNN tend to be majority voting. The majority class of the k neighboring instance of the input instance decides the class of the input instance. Okay, next, as shown in the figure above, there are two different classes of sample data, which are represented using small blue squares and red triangles, and the data represented by the green circle in the middle of the figure is the data to be classified. So how we classify this green circle? What is the category of green circle? If we use the KNN algorithm and suppose k equals to 3, we can find that its three nearest neighbors are one small blue square and two red triangles. So according to the KNN algorithm, the minority follows the majority. We will decide that the point to be classified belongs to the class of red triangle. And when k equals to 5, we can find its nearest neighbors are three blue small squares and two red triangles. According to the KNN algorithm, the points need to be classified. We can classify it to belongs to the category of small blue squares. So according to this problem, we will find out the importance of the choice of k. The categorization results will be affected by the different choice of k values. When the values of k is too small, the prediction results will be very sensitive to the instance points of the near neighbor and will be easily affected by noise and overfitting. When the value of k is too large, it has advantage of reducing the estimation error of learning, but it suffers from the problem of sample balance and the approximation error of the existing training set will become larger. It is often necessary to evaluate the performance of the model under different values by methods such as cross-validation to determine the k-value for a specific problems. And now let's look at another problem. Suppose that I have a house with 3 bedrooms and I want to know how much I can rent it for. So I need to find out how much other people are renting the same house for. So let's look at the first picture. We want to know the price of my house, and this red circle is my house. When k equals to 3, we want to find 3 neighbors that is closest to mine. So we find these 3 circles, three green circles. And when k equals to 5, we find 5 green circles. And when k equals to 7, we find these 7 green dots, green circles. And if we want to know our house's price, we need to find out this its neighbor's price, its neighbor's house price. And suppose we only have 5 pieces of information in our data source. Now I want to set the price for my house, which has only 1 room. And here we assume that k equals to 3. So we will choose 3 neighbors from these 5 pieces of information in our data source. That is, we choose these 3 properties that are most similar to mine, and then, according to their price, we can consider the price of these 3 houses together, and according to these 3 price, I can know how much my house worth. So finally, how do we define which instance is closest to us? Like how we choose these green circles, to be our closest neighbors. So how we define this distance? This requires that we know the distance metric. The distance metric of KNN algorithm is Euclidean distance and Manhattan distance. First one, this is Euclidean distance. Euclidean distance represents the straight line distance between points A and point B on a 2-dimensional plane. And the next one is Manhattan distance. Manhattan distance is different. You can imagine having to drive from one place to another place in Manhattan neighborhood. The driving distance is obviously not a straight line distance between 2 points. And this actual driving distance is the Manhattan distance, and it's also known as the city block distance. So according to these 2 kinds of distance, we can calculate the distance between 2 instances, and we can know, thus we can know which instance are closest to the instance we need to do some prediction.
Okay, let's look at our evaluation index. For our project, we use modeling mainly relies on three evaluation indicators: the R2 score, the mean absolute error, and the mean squared error. First, suppose we use yi to represent the true observations of the data, y bar to represent the average of the true observations, and yi hat to represent the predicted values obtained by the model. Then, first we have SSR, the regression sum of squares. It can be expressed as the sum of the square of yi hat minus y bar. That is the error between the estimated value and the mean, which reflects the sum of the square of deviations from the degree of correlation between the independent variable and the dependent variable. The second one is SSE, the error sum of squares. It can be expressed as the sum of the square of yi minus yi hat. That is the error between the estimated value and the true value. It reflects the degree of fit of the entire model. Next is SST, the total sum of squares. It can be expressed as SSR plus SSE. It equals to the sum of the square of yi minus y bar. Next is R2 is R-squared score. That is the coefficient of determination. It reflects the proportion of the total variation of the dependent variable can be explained by the independent variable through the regression relationship. It has three calculation formula. The first is 1 minus SSE divided SST. The second is 1 minus the sum of yi minus yi hat square and divided the sum of yi minus y bar square. The third formula is 1 minus the sum of the square of yi minus yi hat divided the sum of the square of yi minus y bar divided n is equal to 1 minus MSE divided VAR. At this time, the numerator become our commonly used evaluation index. The mean squared error MSE, and the denominator becomes the variance VAR. R-squared score is between 0 and 1. The closer to 1, the better performance. Here, we only focus on R-squared score. It is the coefficient of determination. In statistics, it's used to measure the proportion of the variation of the dependent variable that can be explained by the independent variable. So, as to judge the explanatory power of the regression model for simple linear regression, regression. The coefficient of the determination is the square of the sample correlation coefficient. When other regression-independent variables are added, the coefficient of the determination becomes the square of the multiple correlation coefficient accordingly. Mean absolute error in statistics is a measure of the error between paired observations, expressing the same phenomenon. Examples of V versus X included predicted versus observed, subsequent versus initial, and one measurement technique versus another. The mean absolute error, MAE, is calculated as the sum of absolute error divided by the sample size. Next is our input. Let's see this picture. The first shows the 10,682 rows and 34 columns. It has its informations, and our project input have 11 features. That is total stops, route, different airline corporations, and the journal date, journal month, the arrival time, and the duration hour and duration time. We divided the processed data into training set and test set, training the model, and then use the model to make predictions. We get scores of these three models mentioned above. The first is a random forest model. We can see in the first picture, it has the R-square score is approximately 0.84. And the second one is K-neighborhood model. It has the R-square score is approximately 0.65. And the third one, SVR model. It has a R-square score is approximately 0.05. And we get the scores for the three models. The first random forest score is of 0.95, and the KNN have a score of 0.84, and SVR for the score of 0.03. We can see no matter for what score, the random forest is the best performance. So the overall performance, we can see the random forest model performance the best. This is our output. We can see most predictions and true values are in the range of -1,000 to 1,000, which is considered acceptable. The residue histogram also basically conforms to the normal distribution, so it indicating that our model is effective.